Hare Krishna everyone. So welcome to a new lecture series on Dirac delta function. Okay. Today we will see the Dirac delta function. Before going into Dirac delta function, I want to derive it from your Gauss divergence theorem. Let's see how do we derive from Gauss divergence theorem. Remember one thing, I'm doing all these lecture series for your better understanding of physics. Okay. And whatever you have doubt, you can ask me without any hesitation. I'm always there to help you. Okay. And you can give me feedback so that I will improve, because every human being need to be improved. I can also improve. Okay. So let me start with your Gauss divergence theorem. You know the Gauss divergence theorem. It says that if I have a vector and the integration over surface, that is A dot ds, will be equal to your volume and divergence of a vector dot dv, isn't it? Yes. So let me take let a vector is equal to your r cap upon r square. Okay. So LHS of the equation, give it a equation, give it a equation number 1. So LHS of the equation will be equal to your LHS is equal to your integration over a dot ds, isn't it? Yes. Put the value of a here. A we have r cap upon r square, and ds take the spherical coordinate system. In spherical coordinate system, the surface ds vector we have r square sine theta d theta d phi. Okay, r square sine theta d phi r cap. Okay, I am taking the plane that is theta and phi, and in the direction of the surface vector is along the direction of r cap. Okay, and the limit will be your 0 to 2 pi, that is your limit of phi, and your limit of theta is equal to 0 to phi, isn't it? Yes. You know the spherical coordinate system. If you will comment that we want to know the spherical coordinate system and Cartesian coordinate system and your cylindrical coordinate system, then I will definitely make a video on that. Okay. With I want always to crystal clear your concept. Okay. So it will become 0 to phi, 0 to 2 phi, and this one will become r square getting cancelled. It will become your sine theta d phi. Okay. So putting the limits, you get minus cos theta 0 to your phi, and d phi is your phi, integration of d phi is your phi, and it will become your phi limit is 0 to 2 pi. So what do you get? You get, by putting the limits, cos pi is minus 1, so minus minus plus, so 1 plus 1 is equal to your 2 into 2 pi. So it will become your 4 pi, isn't it? Give it a equation number 2. You got the LHS as 4 pi. Let's move into your RHS. RHS, what does it say? Del dot A into dv, isn't it? Del dot A into dv. So del dot A will become what? Put the value of your A vector, that is your r cap upon r square. Okay, r cap upon r square. You know the divergence formula. Put the divergence formula, 1 upon r square sine theta, that is 1 upon h1 h2 h3. Okay, into your del upon del r of 1 upon r square into r square sine theta, isn't it? Because I have only here the r component, theta and phi component are absent in your a vector. That's why I have only taken the divergence of your r cap. Okay. So what you will get from here? 1 upon r square. Okay. And r square here getting cancelled, and sine theta, it will become your del upon del r of 1. Okay. So it will become your 0 upon r square. Give it a equation number 3. Okay. So if you further solve it, you will get the value that is 0. Okay, 0 upon r square, that is 0. You can also write it as 1 upon r square sine theta. Okay, 1 upon r square sine theta. Okay, I have cancelled. Okay, from here you get sine theta and sine theta getting cancelled, and we have only your 1 upon r square into 0, that is your 0. So RHS is equal to your 0, that is for r does not equal to 0. It is only possible if your denominator r square is not equal to 0. That means r does not equal to 0. Give it a equation number 4, isn't it? Yes. So RHS part, so what do we get from here? RHS part is not included. We are saying that RHS part is only correct when it is not included your r is equal to 0 point. Okay, it means it is a situation like, we can take a situation that shows us, that will help us understand where we are not including your r is equal to 0 point. So take a situation like this. Let me change the color of the pen. That is charge density of a point charge in a sphere of radius r, okay. Let me draw the sphere for you. So this is my sphere where the radius is your r, and this is your point, that is r is equal to 0 point. Okay, and I have a charge plus q here. Okay, so if I will have to write the charge density, what I will write? If I will have to write the charge density, then I can write it charge density as your charge upon unit volume, isn't it? Unit volume, that is q upon v. So charge density, that is rho, is infinity at r is equal to 0 and 0 at r does not equal. Do you understand it? Yes. I mean that your charge density is infinity whenever your r is equal to 0. You know that in a spherical charge distribution or in a sphere, at origin your charge density is infinity, because at origin, that is r is equal to 0, and it is 0 when r does not equal to 0, because I have the plus q charge only concentrated at the center. Okay, to understand this situation, we define a function. Okay, so in order to understand these situations, like we define a function, a special function such that your del x, that is the function, is infinity at x is equal to 0 and 0 at x does not equal to 0. Okay, that is, this del x is known as your Dirac delta function. Okay, got it? Yes. So how can I represent it graphically? Okay, how can I represent it graphically? You can draw this Dirac delta function by using the Desmos, okay, Desmos graph. Simply you have to go to your desktop, and there from Google Chrome you can open the Desmos site, and you can draw the Dirac delta function. You can find out that this function will look like this. Escape my writing. Okay, this is your x is equal to 0, and this one is your x-axis, and at other points it is infinity value. At x is equal to 0, it has the value infinity. Okay, that is your del x. Okay, I'm just, it is so thin that it is a pointed like. Okay, I'm just showing it for your better visualization. I'm just drawing it like this. Okay, so for the proceeding, I want to tell you about more about your Dirac delta function. So let us talk about your Dirac delta function in detail. Dirac delta function in detail. Okay, so let's start. Let's start with our discussion of Dirac delta function. Okay, so when f of x is a well-defined function at x is equal to x naught, that at that point we can define minus infinity to infinity del x minus x naught into f of x dx is equal to your f of x naught and limit minus infinity to plus infinity del x minus x naught dx. It will be equal to your f x naught. Why? Because the Dirac delta function f of x minus x naught has a sharp peak at x is equal to x naught, and I can write it as del x minus x naught is equal to 0 if x does not equal to your x naught, and plus infinity if your x is equal to x naught. Okay, the same thing I have discussed above. So you can write minus infinity to infinity del x minus x naught, and its value will be your 1. Okay, you can define del x minus x naught is a generalization of the Kronecker delta function. Kronecker delta function. Okay, got it? Yes. Let us talk about some of the principal properties of Dirac delta function. These properties are very useful in your solving questions. Okay, so principal properties of Dirac delta function. Okay, let me start. The first property is del x is equal to your del minus x. Okay, second property is your del ax, where a is a scalar quantity, that is 1 upon a the magnitude del of x, where a does not equal to 0. Except 0 you can take this property. 3. Del g of x is equal to your summation over n 1 upon g dash x of n, okay, xn magnitude into del x minus x naught. Okay, this one is your third property. The fourth property is x del of x is equal to 0. Fifth property, f of x del x minus a is equal to f of a del x minus a. Okay. Sixth property, if you have del x minus y into del y minus a dy is equal to your del x minus a. Okay, you can write it as del x minus a. The seventh one, del x is equal to 1 upon 2 pi integration over minus infinity to infinity your e to the power iota kx dx. You can write it as this form also. This one is known as your Fourier transform. If you have already studied in your BSc, you can know this one. We represent del x as your 1 upon 2 pi into integration over minus infinity to infinity e to the power iota kx dx. This one is known as your Fourier transform. Let me derive one of the properties for you. I will derive one and you have to do the rest. If you have any doubt, you can ask in the comment box. I will do a video on the derivations also. Okay. Don't hesitate to ask me questions. Okay. You ask questions, I will be happy to answer your questions. Okay. And do subscribe to the channel. Okay. So that it will help me make more conceptual videos for you. So let us start with our derivation of del x is equal to del of minus x. In this type of derivation, remember we have to take I1 and I2 to prove all this, and we will from I2 we can derive the I1. Okay, let us consider minus infinity to infinity del x f of x dx is equal to your f of o. Okay, because your x0 is your 0. Okay, by putting that y is equal to minus x, so dy equal to minus dx. So I2, take I2 as your minus infinity to infinity del of minus x f of x dx. Okay, so I can write in place of minus x as y, and in place of x I can write minus y, and in place of dx I can write minus dy. So what it will become? Minus infinity to infinity del y f of minus y dy. Okay, dy is equal to your how much? See, from here you can see that we got the general form of I1 from here. Okay, that is your del y f of minus y dy is equal to your how much? If I will have to write this, I can write it as your f of o, isn't it? Yes. So this one is your I1, this one is your I1. Thus we have del of minus x is equal to del of x. Okay, I derived the first property. I have given you the task of deriving the 6 more. Okay, if you have any problem you can ask in doubt box. Okay, I will definitely happy to solve your problems. Okay, thank you very much for watching. Keep supporting. Thank you for all the loves shown by you. Thank you.